Okay, welcome everybody. Welcome to August C++ meetup. I haven't gave any presentation in a year or so, so forgive me if I'm going slow in some places. Today's topic is introduction to borrow checking in C++. And you will see that there will be actually more Rust snippets than C++ ones. But first things first, I would like to thank Dusan for enabling us to be in this venue. We are in one of the tallest buildings in Belgrade with a very nice view. So probably for all future events, this will be our new place, at least for a couple more events in the future. So without further ado, let's go with our topic. First, can you tell me, did you hear already about borrow checking and borrowing in Rust, especially? Who has heard about it? Okay. Approximately 30% people here heard about it. This is a first concept that we will talk about, and we will talk a little bit about Rust ownership, references, and of course borrowing. And regarding ownership is something that is also a very familiar thing for C++ developers as well. I mean, I think that every seasoned C++ developer who is doing C++ more than 5 years has encountered a lot of problems with ownership in some sense. And with smart pointers and all of the other stuff that we now have in new C++, expressing ownership is sometimes hard. Of course, Rust took a little bit different approach, but as you will see, it's not so much different from the C++ with respect to some other languages around. So Rust, we can say that Rust is pretty much similar in that sense, but it has some differences. So as you see here, what I wrote, each value in Rust has an owner, and this is one of the important things. Rust is very explicit about ownership, and the default case is when you assign one variable, and I'm intentionally saying variable, to another variable, you're actually moving ownership. So it's the default case for C++ is copying, and in Rust for C++ developers, it's actually a move operation. So you are moving objects to the other one. There can be only one owner at a time. And that is also one important thing, as we will see later for some use cases. It is a good thing to have only one owner, because you can have some nice local reasonings, and of course, compiler can help you in some cases when you have that constraint. And maybe it's not a good thing to say that it's a constraint. Actually, in many times it's a very good thing. And this is something similar as in C++. When the owner goes out of scope, the value will be dropped. The value will be destructed. So this is pretty much the same as in C++. When object goes out of scope, it will be destroyed. Being that if it's a plain old data type, or I don't know, maybe a stack pointer will be just adjusted. If it's a user-defined type, of course, destructor will be called, and that is the same thing as in Rust. Rust also has two types of raw, I would say raw references. And one disclaimer, I'm not a Rust developer, so for any Rust developers here, excuse me about saying something imprecise, you can correct me. But the most prominent are classic non-mutable and mutable references in Rust. And of course, in C++, we have counterparts, sort of. We have const references, references to const objects, and references to non-const objects. But we will see that in Rust they're a little bit more powerful and tied to the compiler itself and to some compiler checks. So here is a small example, and this is from the Rust book, Rust reference, how we can actually use references in Rust. So for every one of you who is doing C++, this is a pretty much natural thing. The type of reference that we are using here is a non-mutable reference, and what we can do, we can only use read-only methods for this for objects, and in this case, we are only taking the length of the string. So this is pretty much straightforward. Of course, if we want to modify a value that is passed to a function, we have to use, like in C++, where we will use non-mutable reference. Here also, we use non-mutable reference, and we are able to modify the original string with some other function. And so far, this pretty much looks like one-on-one mapping with what we can do in C++. But there are some further, again, constraints in Rust, and that is that at any given time, you can have only mutable reference, or if you don't have a mutable reference, you can have a bunch of non-mutable references to an object. For the sake of simplicity of this talk, because this talk is intentionally named Introduction to Borrow Checking, because it's a very broad topic, and I just scratched it a little bit in Rust, and I also just scratched it a little bit in C++ as well. There are some user-defined types in Rust, if I'm right, that can be used also as references that are checked in runtime, not only in compile time. But for now, we are talking only about the ref cell and some other stuff that can be used in runtime. But for now, we are only talking about raw references in Rust and something that is checked at compile time. And the other constraint is that all references must be always valid. And then we have a borrowing. That is maybe a new term for C++ developers when they first encounter Rust. And the plain and simple definition of this is that this is an action of creating a reference to something. In Rust, basically, this is called borrowing. So what we had in the previous examples, when you pass a variable to a function, okay, being that you pass to a function that receives non-mutable or mutable references, we actually borrowed the value to that particular function. And now let's go and see what will happen in some other use cases. So this is the similar cases as before, but this time this will produce an error because we are actually trying to modify a string while passing it as a non-mutable reference. So this will produce compile time error in Rust. This one is okay. So we actually need to modify the declaration and to pass the object as a mutable reference. Here is a demonstration of the other constraint that we already mentioned, and that is that at any particular time you can have only one mutable reference. So in Rust, this is an error, and maybe this is the first difference I would say to the C++ itself. So in C++, this is allowed. You can have, of course, as many non-mutable references to objects as many as you want. And later on, you will see some examples that there are also some scoping rules, of course, and because these two references here, R1 and R2 are in the same scope, so they exist at the same time. That's why this is not allowed. But of course, if they live in a different scope that are not interleaving, you can have multiple mutable references. And also, what we mentioned as another constraint, you remember, that is that, okay, we have now one mutable reference, but then again, we have two references that are non-mutable, and also this is almost a definition of a data race in this case. So basically, this is not allowed. And these kind of things in Rust helps developers to have some nice errors during a compile time, and to detect actual data races in compile time. And that is something that most C++ developers are drooling about and dreaming about, to have some good static analysis how to prevent memory corruption and data races. And that is the main point why C++ community is trying to see if there is any possibility to implement some form of a borrow checker in C++ as well. So to prevent memory corruption and to prevent data races. These are two main reasons. While we are at the data race, so this is maybe a vague definition of a data race, but it's I would say pretty accurate. So when two or more pointers are accessing the same data at the same time, and one of them, at least one of them, is used to write to the data. Sorry. And of course, if there is no synchronization mechanism, that is the recipe for a data race. So data race, not a race condition. So it's there are different terms. Okay, and if you remember what we said about references in Rust, that at any given time you can have only one mutable reference or any number of immutable ones. Actually, that guarantees us that we will not have a data race. So by the definition we saw before, that actually means no data race.
So yes. The reference, or it's including the scope, so you cannot copy value to another reference object that is, for instance, in a different tab.
To copy, can you repeat, please?
You can't copy the value of reference to another reference in another tab.
You can have a reference, I think, but it's in a different thread, of course. But it's the important thing that if you have at least one mutable reference that is still alive, so reference, which is still not, I'm not talking about the object itself, but reference which is still alive, you cannot have any other immutable references. So there is. This is a bit more advanced topic regarding the lifetimes in Rust, and it's not part of this presentation. Yes, but sorry, just it's not part of this presentation, but you can enforce these things. You move it. It's the idea is if I understood correctly as well. The idea is that you treat every processing as going through some form of a pipeline. So basically, you process the data and you give it away. You give the ownership. Of course, I mean that is the default thing. There is on the other hand, there is explicit way to copy an object. There are Rust traits that you need to implement for your user-defined type in order to be able to copy an object. So it's almost vice versa than in C++. And there is also this other constraint that that is mentioned, that references must always be valid. And interesting corollary is that you can prevent use after free bugs. And as you will see later, a lot of big companies that are using C++ identified that most of memory errors are use after free, okay, use after free, and maybe memory leaks or something like that. So most crashes happens when you have use after free. So these constraints prevent these things: data race and use after free, which is very important. This was just a brief mentioning of what is done in Rust, and I would say that this is very important because you will see this enforces us to have check in compile time, and while we are trying to do the same thing in C++, doing the same thing in C++ in compile time is, I think, currently impossible. At least some smarter people, much smarter people than me, says that. Of course, yeah. Although there are some speculations that there is a way to implement some checks in Clang, for example, as plugins, something like ClangTidy is doing, for example, and to be able to detect such things well, if you implement it in compiler, it can be, yeah, it will be only like a warning. What can we do in C++, or what is done so far in C++? There is a one document, and it's talking about, and it's called lifetime safety. And I think it's pretty old stuff, right? Somewhere from 2015, and Herb Sutter was, I think, one of the first who introduced this concept. And afterwards, some of implementations of some lifetime checks and mostly use after free checks were implemented in major compilers. And now I think that Clang, of course, and also GCC has warnings for use after free. But in some sense, these are limited use cases, so they do not prevent other classes of memory corruptions and memory errors, and especially they do not prevent so much data races, what we talked about. Yeah.
What exactly do they check? Just a local scope, the pointers.
It's a bit more. It can be a bit more complex than a plain local scope. I mean, one scope. They can check if assigning, for example, assigning to a pointer which already is out of the scope is happening. So if something like that happens, you can get a warning. Yeah.
basically so they have no that.
Also, there is PVS, yeah, PVS Studio, yes, something like that. I mean, just like that. Also, there is a project. I mean, in Google Chromium, Google Chrome, there is a dedicated team that was involved in a research regarding borrow checking in C++. And their conclusion was that it's not possible to implement fully a compile time borrow checker in C++. But they made some progress, and they gave some ideas. What are the constraints in C++? Maybe how can they be resolved, and maybe we will see sometimes also borrow checking. Okay.
Yes.
Yes. I think that I've mentioned it in the last page of presentation, or something like that. To have annotations, lifetime annotations, basically like in Rust. So they're almost one-to-one mapping as in Rust. I saw that, but I don't know what's the current status of that. But sorry. Yeah, but annotations are needed in order to better explain to the compiler what is the relationship between references and between arguments and the return value and so on. Also, there are some tryouts and some implementations of borrow checking that I saw on GitHub. And my main motivation for starting with borrow checking investigation C++ is completely other topic. I had some other use case that I wanted to have borrow checking for, and that is what I call conditional move. When you want to pass an object later on in the pipeline to someone, but and you want to conditionally move it, so not to have it unconditionally moved. Let's say that the next step in the pipeline throws some kind of error. You want to be able to retrieve that object back that you moved in that step in the pipeline, and maybe to give it to somebody else. I don't know. Maybe. Of course, as I talked with some folks here, it's not the proper way to solve your problem. Proper way would be to restructure the code in order to get, again, linear pipeline, and not to have this kind of branching that you're returning back from some step in the pipeline, returning back, and then going to some other branch. So if you can avoid, if you can restructure your code in order to avoid going back in the previous state in the pipeline, that would be a better thing to do. But that was my motivation why I started with this. And this is a picture from Google Chromium team, and I think that correctly describes the state transition of borrowing in Rust. If there are Rust developers, you can correct me if this is. You can say to me if this is not okay. But what we see here is that first object is created, and we are immediately in. We have a unique ownership of it. Then we can transit to one state that we already mentioned, that is that you can have only one mutable reference to that object. This is the state on the left. Of course, the other state is that you can have as many immutable references as many as you like, and these two circles describe that. So the first one has ref T1. This is when you have, this is a base case when you have only one immutable reference. Of course, you can transit to as many immutable references as you want. But what is important here is that you have to always come back to the previous to the previous state to come back to unique ownership. So if you have immutable references, you have strictly to come back to unique ownership only, and then to transit to the other state, and to the state where you have immutable references. And of course, the last but not least, the important state is the destroyed state, and you can destroy an object only if you're a unique owner of that object. If there are some other references that are still pointing to an object, if you borrowed somebody something, you cannot destroy it, and you will be warned about that. So this is a state transition in Rust mainly. So because in C++, we do not, let's say, still do not have a proper way to implement it in a compiler. You have to somehow describe these states using the C++ type system. So as you can see, these are plain. You can have some plain structs, plain small classes. They don't need to have any particular implementation. They are just here to describe state in which you are currently. So they do not need to explicitly hold an object itself. So they are just describing the transitions. But how to we want compile time check. You have to use C++ type system then to describe something like that. So far, I think that this is clear. And also, because references require some explicit lifetime, in Rust we have lifetimes annotation. Somebody is here. Okay. In Rust we have lifetime annotations, but in C++, because we don't have that, at least not yet, then we need to use again some types to describe that as well. And let's explain this a little bit. So now we have to make some transitions. Okay, some transitions from one state to the other. And what they did is they made these kind of functions. And this, let's say that a mute function here accepts unique state, okay? And then it returns a pair of two objects. First one in this pair just describes in which state you are on a type system level. It doesn't hold the object. And the other part of the pair is the actual object through which you can access to the object itself. Okay. And as you can see, the other function ref takes again unique object and returns a similar thing. It returns initially T1 state. That means you created one first immutable reference, okay? And ref of T will hold the pointer to the actual object. Yes?
Unique holds the state, not passive or those don't have anything, those are just empty text, right?
Yes, they are just describing the transitions. I mean, there is some vague naming over there. They renamed it later on, and it's not called unique. I think it's called owned, something like that. But potato, potato. The thing is that we will not mention more than one immutable reference here, because it doesn't matter if you solve the case. Well, it matters, but let's say that if you solve the case with one immutable reference, you can solve the case for many more immutable references. Yes.
What stops some using the same unique to obtain two different?
That are the problems, and that is the thing why we cannot have a compile time check, yeah, as you will. You can, of course. You have a value.
Actually, seems to me that something this thing is plus, because you do have ref. So if you say that you have the whole object, which is like the first case, you
yep.
say that all methods implements the ref purpose, then you're clearly defining that it cannot be called multiple times. Because one
unfortunately, you can bypass and you can store ref. No, but at least you can bind const reference to the R value reference, and that is, let's say, the prettiest way of bypassing. But you bypass the system, and you can invalidate borrow checking just on that basis, unfortunately. I mean, as we will mention just a little bit later, there are problems that are currently, I think, there is no clean solution, or at least standard solution in C++, that would enable you to treat a reference, I mean, variable, whatever it is, that after one time it's used, that you cannot use it anymore. So this is, in C++, this is not the case, unfortunately. And let's say that besides functions that are creating references, we have some functions that transit back to the unique ownership. So let's say you have some, I mean, they call it consumer, whatever it is. You use that pair that you got, okay, and then you do whatever you want with that variable, whatever you can and want, and then you give back the ownership. I mean, you transit back to the unique state. But as you can see, what the signatures here are very important, because we are returning everything by value. We are not using C++ references here. So we are using C++ type system to describe states from Rust and mutable and immutable references. But as you can see, we are not using C++ references here. And because of that, let's say this unique object that you got from the consume function is actually different. It's not the original one that you started with, and that also holds some problems. So, what are the failures of this approach? At least the team at Google concluded that destructors, we will go through that. Non-destructive moves and leftover states. What is the most prominent topic here? I think that non-destructive moves is something that it was the hottest subject from all of these in past few years. Disregarding Rust, C++ lacks non-destructive moves for some other things as well, not only for implementing borrow checking. So it's a broader topic. And what about destructors? When you try to transit to some state, let's say that you create a mutable reference, or you create immutable reference. The problem is that when you consume them, okay, they need to be transferred back to the unique unique ownership. But unfortunately, these types also have their own destructors. And in order to be able to fully control the transition between the states, that you are the only one who can transit and who can even destroy these newly created states, the destructors of these types mustn't be publicly available. So that's, let's say, one of the constraints. And you also see these two bullets here that if these types are destructible, but in first case, if they do not destroy the underlying type, then it can happen that you, for example, have this hasref of T, okay? And because it's publicly destructible, you destroy it, and that object by the first bullet doesn't destroy the object itself, then you kind of lost that state, and you lost the information that you have a reference. And in that sense, you can leak the object. You cannot go back. I mean, you don't know how to go back anymore. And also vice versa. In the other case, when they do destroy the underlying object, you can enter the use after free scenario, and that's the problem. And as I mentioned, only if you have these destructors not publicly available, you will be in a full control how you want to transit back them to the unique state. Otherwise, you will have a compilation error if these objects try to go out of scope without you. The other problem is non-destructive moves. And this is, as I mentioned, a little bit broader topic. And that is the case when you move out from the object in C++. The moved from object is still something that has to be left in a valid, but unspecified state, if I say, or yes, in a valid but unspecified state. I'm trying to quote the standard here. What it means to be in a valid state in this case for a moved from object. That means that at least you're allowed to assign something again to that variable. So if you moved from a C++ object, you don't care for the state of that object, let's say, for its invariance and so on, but you are able to assign back to that variable. And not only that, moved from object will have his destructor invoked for sure, and that is guaranteed. So basically, you're making transitions from one state to the other, and you have like these side effects that you have destructors for some of these states being called when you moved from objects. In Rust, that is not the case. In Rust, if you move from one object, which in Rust looks like a simple assignment, the moved from object variable from the compiler perspective is completely destroyed. You cannot do anything about it later on. And that is why because Rust has destructive moves, and in Rust you cannot enter in use after free scenario, and in Rust there is no invocation of a destructor for moved from object. You can have Rust move operation implemented as a plain mem copy. In C++, that's not the case, and there is a prominent example for, let's say, if it's his favorite linked lists, and that is when you have a node in a list, which is a sentinel, which is the, let's say, last one. That sentinel still should be dynamically allocated. And it's interesting when you move out from the list node. In that particular case, move operation cannot be plain pointer assignment. It has to do something more, a little bit more, for the moved from object in order to for that object to be in a valid state, at least for the destruction itself. You cannot just leave pointers as it is. And because in that case, maybe these are not too many cases. Move is not a cheap operation in C++. Of course, there are some other cases when move in C++ is not cheap, but from this perspective is the prominent one. And Rust, of course, can afford it himself to do only a mem copy, because nothing will be invoked for a move from object. And because destructor is needed for moved from object to be called, and it's needed to be public, okay? That violates the previous condition that we mentioned, and that is that we want to have private destructors in order to be able to control state transition. And that is the let's say one of the clashes why we cannot implement it so easily. I will mention some. I linked some posts for non-destructive moves and some proposal as well, and one beautiful article from Sean Parent about it. He wrote about non-destructive moves almost 10 years ago, or something like that. It's a nice read for anyone who wants to know what it's about. Also, one of the problems that I mentioned also are leftover states. Let's say that you want to come back from reference to unique ownership. As I mentioned, because we are not using C++ references, we are returning values. So you will create different unique T object. But what will happen with the one that you started with? Let's say you start from one unique T, okay? You create your reference, and then you consume it. You get back some other unique T. But what will happen with the original one? With the original one, there is a problem because we don't want for it to be used. Because if we allow for it to be used, we are breaking some implementation of borrow checking, because we can use transition functions to again transit from that original unique T to the other states, which is not a valid thing. Yes. That's a dynamic check. And of course, that's the part of the problem. I think that it cannot be like that. And there is a problem. There is a problem because all of these types, which are marking only the state transition, they are not bound to a particular object. They are bound to a particular type. So also you have, you can, unfortunately, you cannot enforce some mix and match of these state objects, so to say. You have to be careful also about that. And that is also one of the reasons why you cannot implement it this way. And I think this is one of the last problems mentioned. And that is, you saw one of the first snippets in Rust when we pass an object as a reference. Rust guarantees, at least even if you don't choose, in a simple case, even if you don't choose lifetime annotations or something like that, Rust guarantees that this reference has a particular lifetime, okay, and that you have to return it back. You cannot steal the reference in Rust from some scope to another. Its lifetime is kind of guaranteed. In C++, you don't have such guarantees. Basically, you need to return back. If you use mutable reference, for example, you have to consume it, access the object through it, whatever, but you have to return it back. To store reference, oh, yes, but you have to create one more that you will store. That is completely another scope then. So the problem is that that will be completely different. I think that will be completely different object. I think that you will not have problem to do that. But if you use if you consume particular mutable reference that I pass to you, when you are done with it, you have to return it back. I mean, in the object, if you want to store it in the object, you can, but you have to have a way that when that object goes out of scope, that you return that reference back. So now you can decide if that is easy or not so easy for you, you know. What exactly?
So if I store a reference in an object.
No, I mean these state objects in C++, like mutref of t, are plain, let's say plain structs, plain objects. If you okay.
Is it in Rust possible to store a reference in an object?
Yes, I think yes. Of course. Yes, I mean, or it can, correct me if I'm wrong, to inherit. I think that enclosing object and the reference itself, yeah, and to have at least lifetime of no, enclosing object have to have at least. Mm-hmm. And
doesn't mean any lifetime holds all
values. Yeah.
For example, about hash maps. Your key could be either a reference to some, say, string or whatever, or it could be some object like key. So try to you always know that these hash map references treated accordingly. That would hold longer. It needs to live as long as
yes, at least as long as enclosing object needs to live at least as yeah, this one.
Pretty much not, but Python guarantees that you can select objects in wrong direction. So you always know how to compare lifetimes, which should be bigger than not one. You always can reconstruct it.
Yeah, so I think that's the hard part. While you're getting close, we don't understand, we're going to do anything.
That's probably the hardest part of it. So somebody
mentioned the paper there is going on currently. I briefly just saw that you can have attributes in Clang that will mimic sort of lifetimes that exist in Rust, but I'm not completely sure how it works. But in this case, what I've mentioned, because you have to return back this reference in order to keep track of its lifetime in that way, you have an ugly API, at least. So you don't have some, I mean, maybe it's not so ugly, but it's very noisy. And I think that we are approaching to the end, but I will show you some example that I found on GitHub that was that was interesting to me. I tried to write on my own some borrow checking in runtime, not in compile time. I just wanted to do that in runtime. Meanwhile, I saw one of the implementations which are not maybe super cool or super efficient or whatever. None of these implementations are probably super efficient, but there are some good ideas. So I think that I can go to that. Okay, I don't know if you see, if it can be seen on the video, or probably. Okay. I attached the link to this GitHub project. You can go through on its own. The idea again is to somehow describe immutable and mutable references. And in a nutshell, what this guy did is he created some form of wrappers, reference wrappers around the objects, one a non-const and one const pointer. Okay. So this is a mutable one. Of course, accessors and so on. And there is some internal counter that counts them in some way. He was a little bit smarter to use one counter for both of them, for mutable and immutable reference. So whenever you create, I think, mutable reference, you will decrease the counter, and it's a hacky thing, but it gets you the result. And when you create immutable reference, he increases that counter, and based on that, he has some asserts in which state he is at the moment. And of course, there is a wrapper for owning an object. So this is one. This is the one. And the implementation here at this moment is not so important. You will have the link, but what is important is these tests, let's say, and we can build it. Okay, we can execute it. Let's. Okay, sorry. And we have in one of the tests we have borrow checker violation, and you will see where. So, for example, what happened here? We have an owner. Okay, owner holds plain integer, and we first borrowed mutably borrowed from it, but as you can see, this is in one scope, and then in the outer scope we have second mutable borrow, and this is the thing that goes out, and that is another mutable borrow, but which will happen after this one, which is an actual violation. So here you are trying at this point to create another mutable reference while this one still exists. And in this implementation, what he did is abort. And sometimes I think it's a good thing. So very early failure. So if you have these are all, of course, runtime checks. But if you have a violation, you will abort as early as you can. He, of course, predefined this macro. So basically, you can do whatever you want. He did the abort here, but you can implement this borrow verify to do whatever you want. So let's go maybe with some other tests. That I've commented. Let's go with this. I don't know. I'm not sure if it's valid or not. What do we have here? Again, this will be something that is not valid. And of course, we will have borrow checker violation again. Why? Of course, we have two mutable references. And do we have a valid test? No. Okay, we can create at least one valid test. So the third one will also fail, I think. And this is so this is the place where you have one mutable, but unfortunately you have also in this case two immutable references. So two immutable and one mutable. So if I comment this out, this test should be valid. Yeah, so nothing was printed out. So that means it's okay. So this is just one of the examples that I saw on GitHub. Of course, there are other ways, many other ways. If you are in a runtime, there are many other ways to implement some form of borrow checking. This one was interesting to me because I think his focus was on static analysis tools. I didn't use it before. I tried to set up it on my machine, but I failed. Facebook Infer. I don't know if somebody used it. No, Facebook Infer. I think that the statement is that they've gone a little bit further with lifetime checks with that static tool analyzer. So he used Facebook Infer just as a plain static analysis tool, and his own implementation, this one, and the tool was able in 95% of the cases with some false positives to tell him that he has a violation while he was doing static analysis of this code. Personally, this is quite good. I mean, I immediately imagined that you can have these kind of things in some while you're debugging your project, and that you can decay to normal types in a production. So you can kind of have in compile time switch or some macro which will control that you can use these types in debug mode, let's say, and use plain types and normal things when you're in some release mode or something like that. And in combination with static analysis, there are pretty good results. But again, this is not a compiler and this is not a compile time check. It's just making much more easier for the tools to detect such problems. And just a second. Yeah, so here are some references, not Rust ones. Lifetime safety that I've mentioned. Then this borrowing trouble that I also described a little bit from Google Chromium team. There is a proposal for destructive move, and this is for C++ seasoned C++ developers. This is informative read to get to know what it is about. The same thing is with the Sean Parent's article about move. Of course, snippets were from references and borrowing from Rust documentation. And there is an interesting article. I surpassed 1 hour, and I said to myself that this will not last more than 1 hour. But sorry, this 1 hour exactly right now. So there is an interesting article called "Almost Affine." It describes affine types. I think that's a wrong naming for any mathematician here. He or she would kill me right now if I use affine for something else than what it's meant to be. So what are affine types? Affine types that are, the definition is very simple. These are types that can be used only once. So you can easily imagine our use case over there in what we mentioned. So use only once, and afterwards you cannot use it anymore. So in this article there is a little bit broader discussion how maybe to implement affine types in C++.
Actually, all compilers.
Sorry.
You're able to implement affine types.
Yes, and that is the last link I think here. If you thought about it, the exploit for stateful metaprogramming, and the thing that you can have in at least 3 major compilers, that you can keep the state, and you can control. For example, how many times you called your member function. So
specifically when standards described as something which could not be relied on.
It is, but in the new standard in C++20, when the added support for non-temporal or broader non-temporal arguments, you have other references to the same thing.
So this is.
Is it still intended standard for avoid that?
No. You can now use that as well, but I think it's implemented in a different way. So the thing here that I'm showing you right now. Sir. Yes. Yes. Okay. We will not go through this implementation right now, but the idea is that you can, for example, call one method only once, and you can even have counters how many times you call some method, and you cannot check all that in compile time. So this is not that implementation, but there is an implementation that uses a stateful behavior of metaprograms to implement compile time counter, and basically you can do whatever you want. You can choose to have an object for which you can call function exactly 3 times, and not less or not more than that, and something like that. It's crazy. It's relatively new that new thing that I saw, but it's nice. So you can try this out. You can try this out. I think that I found this as a new implementation for what you mentioned. No. You can specify for any function how many times for that function is allowed to be called. If you have F, G, and H functions in your object, you can choose, for example, you can implement, for example, to have F function that you need to call F function exactly twice, G exactly once, for example, and I don't know, the other ones, whatever you want.
Yeah, but it can be as complex as you want. You can create a state machine where you say that you first need to call function F and then you need to call the function
Yes,
G.
of course. You can create a graph of whatever you want.
Another thing that you implement is, so C has so in C you have an ability to say that arguments in the same function are not going to be alias. Implement the alias with the state format problem. Basically, you do it in a way that each instantiation of type is a different type, so that you could see whether the two things that were actually passed through the function are pointing to different objects. So once you have a state format problem, you can end.
Basically, that's the case.
I'm not saying.
And with that, I would like to thank you. Thank you very much, and I hope that we will see next month in this beautiful space. And now you can enjoy the view. Thank you.